thought it would be time to give you an update on how a wind tunnel works. For those of you who are interested in how a wind tunnel works, wind tunnels have been around for a long time now, more than 100 years. The first one was built by Gustav Eiffel in about 1906, and the design of wind tunnels can vary quite a lot. For example, you could use a bit of a bell mouth, if you like, a trumpet, to allow air to come into a working section, then have a working section, a little bit of a diffuser, and then some fans. And then you can put that whole package just like that into a building and allow the air to find its own way back around the building and back through the working section again. It's a system that's low cost to build, but no Formula One team uses a facility like that, basically because it's quite expensive to run. So it's cheap to build, but expensive to run. And one of the reasons that we use what we call a closed circuit, a circuit that takes the air around a loop, is so that we can continue to use some of the energy we put into the air to drive it around the wind tunnel. We reuse that air. It's just a more efficient way of using the electricity that we use to drive the air around the wind tunnel. And the wind tunnel is a sort of an odd looking shape, if you like. We have our fan almost opposite the working section in our circuit. The fan, we have a rather large fan. It's about 3 megawatts of power that allows us to run to about 80 meters a second. The fan is housed on a very large block of concrete. We call it a seismic mass. And the reason is that if you didn't have it mounted on something very, very solid, it would create like a seismic event, an earthquake, because you're using so much power. And no matter how good a job you do with your fan, it'll never be perfectly balanced. It'll be reasonably well balanced, but it's never going to be perfect. So you mount it on a very large mass, and the seismic mass is then mounted on an even bigger mass via effectively, literally, springs and dampers. If you physically go into our wind tunnel and you look at where the fan is mounted, you literally see springs supporting the minor seismic mass. And then the mounting, the foundation for the fan is then a separate foundation from the rest of the building. It sinks down into the ground a very long way, and there's a soft connection between it and the rest of the building. It doesn't stop, it's not large, it's relatively small, the vibrations are quite small, but there are vibrations there that you don't want to go into your building, and in particular you don't want fan vibrations to shake your model, so you have a separate foundation. So just the science of building a wind tunnel in itself is really, it's interesting as if you're an engineer, it's just an interesting science. And then going a little bit more into the air side, the aerodynamic side of the design of a wind tunnel, if we start with the fan, we have the fan, it blows the air along, it creates turbulence, if you like. A fan will tend to take the air and make it rotate because you're rotating the fan blade. So the fan blades are designed to push the air in one direction, but they add some rotation. So after the fan, we have, if you like, anti-rotation vanes that try to then re-straighten the flow. We then also expand the air. You see the airline looks like from the fan it's expanding almost all the way to the working section, then it contracts for the working section, and then after the working section it expands again. And the main reason for that is the efficiency of the use of the air. It takes more energy. If you kept the working section size all the same all the way around the airline, then you actually have a higher build-up of boundary layer. The friction of the air on the walls of the wind tunnel is higher if the velocity is higher. And aerodynamic forces increase with the square of speed, so the friction really is much higher at high speed. So if you gently slow the air down as you send it around the airline, you slightly reduce the losses you get as you send the air around your facility. It means your airline perhaps has to be a little bit larger, so again it increases the cost of building the wind tunnel, but it does then use energy more efficiently. But that's not the only reason. We also have to manage to take the energy we put into the air. So the energy we put into the air, we have a 3 megawatt fan. If you're driving at full speed, those 3 megawatts effectively generate motion. You call it Brownian motion. It generates excitement between the molecules in the airline, and that energy becomes heat. So we heat the air up as we drive it forward, we have to take that heat out of our airline. So in our facility, in one of our legs, we have a huge, really huge radiator. It's about 9 meters by 9 meters in size. We pump water, cool water, through that radiator as fast as we can pump it, and we regulate the temperature of the water. So we send the air through a radiator. This has an additional benefit. Swirling air will pass into a radiator. Once it passes out the other side, you can no longer have, if you like, a big macroscopic swirling of the air. You stop that swirl, send it through the radiator. We then send it through a couple of corners and towards the working section. Now in each corner we have turning vanes. You can think of them as a baffle, but what I would call them a turning vane. So in each corner there are a number of aerofoil shaped or curved devices that help the air to make the corner with the minimum aerodynamic loss of energy. And we have those in every corner. Without it, you just waste a great deal of energy. So this is something that early wind tunnels for over 100 years have used. When we get round to the last leg before we have the working section, we have what is called a settling chamber, and as the air passes into the settling chamber we expand it reasonably quickly. We then have a blockage caused by in some wind tunnels it's the radiator, but we have a radiator and then separated from that a honeycomb, and the honeycomb is aligned so that you just see the edge of the material in the direction of airflow. But any remaining swirl in the air is almost entirely eliminated by passing through a rather long series of effectively rather long thin tubes, so that the air, if it's swirling in the working approaching the working section, that swirl is eliminated. So that's the purpose of having a honeycomb. And then after the honeycomb we have a number of fly wire screens. You can think of them as basically a fine wire mesh, but in tropical countries you'd use them as a screen to prevent insects coming in. I grew up in Australia, so it's a fly wire screen to me. These screens take any remaining large areas of turbulence. It's becoming smaller because it's passed through the honeycomb. They take that and they break it up into even smaller turbulence. And then we have what we call a contraction, a bell mouth, a contraction. It takes the air and compresses it to a smaller size, and we can't create or remove air, so it has to speed up as it approaches the working section. One of the things this does is it takes the remaining tiny little bits of turbulence that are still there after passing through your wire mesh, or your wire meshes, because we have quite a number, takes that remaining turbulence and breaks it down into even smaller turbulence, because it might be a few millimeters, but by the time you compress the air, we have quite a decent contraction ratio, and by the time you compress the air to something even faster and smaller, more together, then that turbulence is reduced even further. And these are tricks that you use in a wind tunnel to keep control over the turbulence level. Now that doesn't mean you don't want to, in certain circumstances, add turbulence back into the air, but that's something we can manage. Then you have the working section, and then the working sections can be quite different. We have a working section where we are able to convert the working section from a closed jet, where the working section is completely contained within walls. That's actually how we operate most of the time. But we are also able, because we have it in what is called a settling chamber, to open up a pair of bell mouths at the back of the working section and convert the working section to slotted wall, or even three-quarter open jet. And three-quarter open jet is a very common type of wind tunnel, used a lot for, say, acoustic wind tunnels in the automotive industry, where you have your jet at the end of your contraction, and the air just finds its own way to a bell mouth at the end of the working section. You put your vehicle in the middle and you get less speed up of the air. Well, you don't get effectively a greater speed up of the air than you would in reality. So in reality, a vehicle will pass through the air and punch the air out of the way as it does. And in a closed jet wind tunnel, you have a restriction, so the air passing over the vehicle is sped up a little bit more than it would be in reality. If you convert to a 3/4 open jet wind tunnel, you don't have that problem anymore. You have some other challenges. With a 3/4 open jet, you start to get a little bit of pulsing in the wind tunnel, initially caused by just the rotation of the fan, and that's quite difficult to take out, and the turbulence quality isn't quite so good as a closed jet. So there are lots of advantages and disadvantages with different types of wind tunnel, and each race team or each wind tunnel manufacturer chooses his own way to do that. Then there is another type of technology which is called contoured wall, which almost nobody uses, because a contoured wall wind tunnel would be make the shape of the wind tunnel the same shape as the air would form if your test body was permanently this type of test body with very minor changes. It would form the air would form a certain natural shape in free stream if you're just punching a vehicle through the air, and you make your wind tunnel form that shape. But if you, for example, want to yaw your model or your car, then you would need a different shape of wall. So contoured wall is not commonly used, but adaptive wall is used quite a bit in motorsport and is a really clever technology, and basically in a very simple way allows for the blockage effect without quite worrying so much about the exact shape. And we don't use that technology in our tunnel, but it's a really good technology and allows a team potentially, or a wind tunnel manufacturer, to make a slightly smaller wind tunnel and use this technology to correct for blockage rather than just make a nice big one so the blockage correction is smaller. And that's the fundamentals, if you like, of the use of the design of a wind tunnel. Now honestly, motorsport teams have taken aircraft and aerospace developed wind tunnel technology and adapted it then for use in motorsport. And I'd say adaptive wall technology is something probably first used for motorsport rather than first used for aerospace, because motorsport teams have tended to put too big a vehicle in too small a wind tunnel and try to get away with it. And this was one of the technologies that the teams have used to find a way around that problem. And that's quite nice technology. And then other things that wind tunnels have, other ways that wind tunnels have changed to suit motorsport more than the aerospace industry is when air passes over any surface, you get a boundary layer growth. So if you blow over a table, then the peak of airspeed is not going to be in contact with the table. It'll be a little distance above, because there's a certain amount of friction between the air and any stationary surface. And all the way around your airline of a wind tunnel, that boundary layer is growing. And one of the things that the contraction does is it also shrinks that boundary layer a little bit. But the boundary layer for racing cars in particular is really important for wind tunnel testing. You don't want it because the boundary layer doesn't exist when a car drives over the road. There is an atmospheric, there is, if you like, a planetary boundary layer for wind, but let's ignore wind for now. That's another thing we don't want to get into too much detail about. But the boundary layer in the wind tunnel is not something you encounter on the racetrack, and so we want to remove it. And that's a boundary layer removal system. There are lots of ways, but a simple way would be create a step, if you like, near the leading edge of the working section and suck off at exactly the right speed any air that is moving more slowly than the air in the free stream. And typically speaking, in a wind tunnel, in a decent sized wind tunnel, it's going to be 40, 50 millimeters, something of that sort, if your wind tunnel is well designed. You can also just put a patch in front of the working section with holes in it and just suck air through that patch, which will draw air down towards it and speed up the airflow near the surface. Then just behind these systems you put your moving ground plane, which is moved at a speed synchronized to the airspeed, and beyond, once you start moving onto your belt, then you no longer have growth of the boundary layer. And these systems were invented by motorsport people, or really not invented. The concept wasn't invented, but they were developed for motorsport teams and made to work really well because of the extreme needs, if you like, of motorsport teams. And now the aircraft and aerospace industry use that technology for things like takeoff and landing, where before they didn't worry about it quite so much. So they're technologies so you get a mix, if you like, of aerospace technology and motorsport technology helping one another to advance our ability to simulate reality in a testing environment. I'm giving the game away now. I'm going to ruin the future of aerodynamics. Looking at the schematic of the test section, you can see that the model, you need to mount your model in some way. So there's lots of technology in a wind tunnel that you can see when you look at the test section. So let's start, for example, with the model motion system. There are lots of different ways of mounting a model in a wind tunnel. The aircraft industry would tend to use a sting that comes into the tail of the aircraft so that you have the minimum aerodynamic interference. Mount systems for wind tunnel models of race cars, we've tried every type of mount that you can think of. Wires suspending the model from above, which is quite difficult to manage, not particularly rigid. It's a technology we'll probably investigate again in the future. A sting coming into the tail, like the aircraft industry we've tried. Mounts either side of the model, mounting the model from arms on the wheels, and in the end, the system that appears to give the least overall aerodynamic interference into the flow around the car is to mount it from above in somewhere around the middle of the model. It's not that we haven't tried other methods, but it's about the most, about the best way. However you organise your model, now we use what's called a hexapod, but however you mount your model, you need to be able to move it up and down. You need to be able to yaw the model. You need to be able to roll it. You need to be able to pitch it. Then we have many other degrees of freedom. For example, you can steer the wheels, but that's we do from the model. The hexapod has certain advantages structurally. It's quite stiff. It allows you to do most of your motion from above. So with a hexapod, you control the roll by moving the hexapod sideways like this. You control pitch by moving the top of the arm fore and aft. Yaw is done lower down. You can do yaw from literally within the model. So you can just decide to yaw it from within. On ours, we have the yaw point a little bit higher up, and we yaw it from a point here. So most of the model support is aerodynamically aligned with the airflow, and only the bottom part moves the model. So these systems are computer controlled, reasonably rigid. They're actually quite heavy, but the weight doesn't really matter unless you start to move really quickly. And we move at a controlled pace. We don't move violently, dynamically quickly, but we move continuously and reasonably quickly. We have wheels mounted on our model. I've worked with both wheels mounted on model and wheels remotely mounted on arms, so that the vibration and the inaccuracy, if you like, caused by the vibration of the wheels is not transmitted to the measurement systems on the model. But we found over time that the absolute accuracy of having wheels mounted on the model outweighs the slight measurement repeatability problems you have when the vibration of the rotating wheels just slightly reduces your ability to repeat precisely a test. And that's been achieved through experimentation. You try both systems, you see which gives you the best results. And now there is such importance placed on the aerodynamics of the wheel and how that changes the airflow around the car that you really, I feel, need wheels on the model. The wheels are turned by the rotating belt. The tyres are supplied by Pirelli as part of our contract with them. All teams are supplied by Pirelli with both their race tyres and their model tyres. The model tyres have their own technology. the tyre supplier does have to think hard about how to design the tyre. It's not just a scaled version of a race car. So we are supplied up to 12 sets of tyres per year to do our wind tunnel testing. And in the past, when wind tunnel testing was not limited, those tyres would have to do of the order of 50 to 100,000, and some sets would do more than 100,000 kilometres of testing in the wind tunnel. A set of race tyres, a race is 300 kilometres long and you have to make pit stops. So the longest you're going to do on a set of tyres is just over 200 kilometres is all a set of race tyres will do. The model tyres have to do, not 100 times, but they have to do a lot. Sorry, not 1,000 times, but nearly. So the tyres have to be different also in their durability, and that means it's quite difficult to simulate exactly what a tyre does on a race car, and that's why Pirelli spend energy designing different model tyres to the tyres that you use on the racetrack. So looking again at the test section, one of the things that has been the subject, one of the areas that have been the subject of quite a lot of research over time has been moving ground technologies. Again, it's an area where motorsport has led the way, and the aircraft and aerospace industries use what we have developed for their takeoff and landing simulations. Now, when I first started working with moving grounds, it was literally like a conveyor belt, almost as crude as a supermarket conveyor belt, just with a lot of tension and then with a bigger motor to run it faster. And one of the first things we learned is that if you do that and you put a race car on top of it, the belt is then sucked up by the suction created by, say, the front wing, the diffuser, even the rear wing will have an impact, but really the front wing in particular. The belt is sucked up, and if you produce a more powerful wing, the belt's sucked up more. That makes the wing work even more efficiently, up to a point where eventually the belt will come up and touch the wing, and then no air can come through, and then suddenly you lose all your performance. So very early on, about 30 years ago or more, actually more, I'm getting older, 30 years ago we learned that you had to then suck the belt down, and these were synthetic belts, just like a fancy supermarket conveyor belt or a running machine belt, for example. And when we then sucked the belt down, and that solved the problem for a short time. But then we found we needed more power, because when you suck the belt down, there's more friction between the belt and the table, if you like, the surface that it runs over. So then you start to put holes all over your surface. You suck the belt down, you create more friction, so you need a more powerful motor. And then we found the belt life would reduce dramatically. And on some occasions, we've literally had a belt melt and stick to the moving ground system. And so then you think, okay, we have to control the suction. So then we started to control the suction. So you apply the suction where the front wing is, and you try and create, nowadays we just use CFD to tell us what the map is of pressure on the surface that we're running on. But in the past we would through experimentation and logic and a bit of aerodynamic knowledge, work out, okay, most of it will be where the front wing is, then you'll have other suction where the diffuser is. And so we then would regulate boxes underneath the belt to control where the suction was. But we still had the problem that we're generating a great deal of heat underneath the belt surface, which would limit. So we went from a belt life of, say, 200 hours to a belt life of 50 hours when we put suction on. So then we decided to go for cooling. So then you take your metal bed for your moving ground system and you start to drill holes. We used to call it gun barrel drilling, because you're drilling a hole over a long distance. So this synthetic belt technology was replaced when an American company called MTS came into the market with a new type of moving ground technology. This technology is basically a steel belt with a highly polished underneath surface, which is supported on air bearings. Now, an air bearing is nothing particularly hard to understand. It is, you supply high pressure air through a microporous material, and this microporous material allows the air to come through. It's still at quite high pressure, so the harder you push down with your steel belt, the more that is resisted by the air pressure coming through the porous bed material. The only problem with that is this porous bed material with lots of air coming through is pushing air underneath your moving belt, and unless you evacuate it, you then have an air bubble that's going to allow the belt to float, and it'll be sucked up. So basically you have about approximately 20 mil wide strips of air bearing, and either side you have vacuum lines. So we have rather large vacuum pumps within the wind tunnel building. To every 20 millimeters it sucks away the air that's being pumped in, so you have air being pumped in, air being pumped out. The interesting thing is that then the horsepower you need to drive your belt reduces dramatically, because the belt is supported on air bearings, and it literally is floating on air. And it was very funny in the stages where you're commissioning your facility, you can take a flat piece of material, such as even a relatively heavy small surface table, turn it upside down. A surface table is very smooth. Turn it upside down and put it on these air bearings, and you can sit on it as a human being and float along. It's a little bit like a two-dimensional version of flying in space, but it's only two-dimensional. But it is quite funny. And this technology has then been evolved and developed and matured. So we now have a moving ground system that is so well engineered that we can put a race car on top. We can take the weight of the car and the aerodynamic downforce of the car, which is much greater than the weight of the car, it's getting into tons, and do aerodynamic testing on our race car up to 80 meters a second, physically possible, not allowed in the rules anymore, used to be, but physically possible, and we have no problem whatsoever with the moving ground system, which with a synthetic belt was an impossible dream, or close to an impossible dream. So this technology has become very, very useful for other industries also, more extreme aircraft industries, to do their testing. So they would now be able to effectively land an aircraft on a belt in scale, of course. So that's moving ground technology, which has changed a lot. And one of the side effects of using this steel belted technology, because the friction is so low now, we no longer need cooling for our moving ground system. It's cooled by the air we pump underneath it. So we use a lot of measurement tools in the wind tunnel, as all teams do. A few that we can describe to understand. The main load cell. Now, what is it? It's a fancy weighing scale is what it is. Now, typically with a load cell, you talk about the percentage repeatability of the measurement. And that a manufacturer of a load cell will give you a specification that this load cell is accurate to 0.02% of the full-scale load. And to expect more than that is being optimistic, but the manufacturers of load cells continue to work to make them better and better and better. So in the model we have a lot of these load cells. The main one we use is a 6-component load cell we use for measuring the overall forces on the car. So we want to measure, for example, the downforce on the car, the side force exerted on the car, and the drag force on the car. But we also want to know, where is the downforce? How much is on the front, how much is on the rear? So you use a pitch moment. So you can separate that out by having a load cell at the front and a load cell at the rear of your block of your 6-component balance, so that you can calculate then what's the downforce on the front and what's the downforce on the rear. Then the same applies for the side force, and the same applies for the drag force and yaw moment. So that's why 6 components. We have a number of 5-component load cells, for example, one for the front wing, one for the rear wing. We could make those 6-component as well, but for us it's enough to measure 5. We have load cells in the axles of the wheels, and we also measure the forces underneath the wheel contact patches. Now that's extraordinarily difficult to do, because between the tyre and the load measurement we have a thick, fast-moving belt system. But despite that, experimentation and calibration has taught us that we can measure the load that the tyre uses to push down onto the belt. We can measure that, by having a specifically carefully designed high pressure air bearing load cell underneath the spot where the tyre exists. And through a lot of work, we've been able to calibrate that so that we can accurately measure. So if you put a car into the wind tunnel, a full-size car or a model, we can measure the load, the weight of the car, let's say, but also the aerodynamic load of the car with quite good accuracy, despite the fact that you've got the belt moving in between. And that's probably one of the more difficult technologies. And then within the model, we have lots of other measurements, position sensors. The model is a relatively sophisticated, very specialized robot, if you like. Lots of motors to move things around, for example, the steer, and then systems to measure how far has the steer moved, systems to measure pressure. We have hundreds and hundreds, and I won't say how many, but we have hundreds and hundreds of pressure sensors measuring the surface pressure on various parts of the model. And this allows us to understand more of the airflow around the model. There are also systems such as laser measurement systems for air movement. They don't actually detect air movement. It's basically laser light, either in a sheet or a few lasers pointing at a single point. You need something visible to use the laser to tell you what's happening with the airflow, but a smoke particle is more than enough to be visible. And as the visible particle moves through a tiny space that's lit up by a special laser light, we can use that to detect the velocity of the air, so the speed and direction, and also the turbulence level of the air. So these are technologies that we don't talk about very much, but these are technologies that exist and we have available for our wind tunnel and we use for our wind tunnel. And I've probably said far too much already. If I say any more, other teams will start looking at this video, which I don't want. Often in a wind tunnel, you'll see, or often when you see pictures of wind tunnel testing, you will see a man with a smoke wand and smoke blowing over the model to look at the nice airflow lines. So you might see a rake of several smoke wands creating a bit of smoke that blows over your test model and allows you to have a look at the airflow. These are useful, but as you gain more and more experience of airflow, they're useful for looking at, if you like, macroscopic overall airflow. We use that technology today for real aerodynamic research, so rarely that we don't even own a smoke generator for visualization, human eye visualization of the smoke. We use the more precise and, if you like, less intrusive. A smoke wand, when you put it into the airflow, already the wand starts to interfere a little bit with the airflow. The fact that you're pushing smoke out of the wand also interferes just subtly with the airflow. So you can use it to look at where is a vortex, where is the air going, the air that goes into the side pod, where does it come from? You can use it, you can move your wand around to try and find where does the air that goes into the side pod come from. That will work. But we have other ways of finding that out. So we actually very rarely use a smoke wand as such in the wind tunnel for genuine aerodynamic research. It's good for the publicity photos. So if you see publicity photos like that, it's a publicity photo. After building this wind tunnel, we used to, while it was still permitted, really test quite often with a full-size car in the tunnel. If you have the money, why wouldn't you? The advantages that had were mainly that we were testing with real parts, full size, high speed, and that the car would then deform in a real way under aerodynamic load. And the main downside to that was the lack of a genuine cornering simulation, and also, honestly, the cost. We also did straight line testing, an airfield type track, no blockage effect, lots of data from one set of constant conditions. That gave us additional information, and averaging data over a long time makes the data, if you like, more repeatable. But again, we had no real corners. And track testing is the closest to racing, but in a test you're also able to control if someone is directly in front of you. You can find yourself some clean air without giving away a position, and that has some real advantages. However, conditions such as the weather, the state of the tyres, the consistent behaviour of the driver, they're things that are changing. However small, they're changing. However subtly, they're changing all the time. So track testing is the most realistic way of testing, but it's also the least repeatable because of these changing conditions. And track testing also wears out the powertrain, wears out the tyres, and so costs much more than other research methods. Model testing costs less. Models look smaller than their linear scale, at least to me. If you see a model, I believe what you see is area. So a 60% model, you see 36%, comes out at 36%. You see 60% of the width, 60% of the height, if you like, and that looks like a bit more than a third of the size of a real car. And for me, that feels correct. It feels definitely smaller looking than a half-size car, even though it's bigger than half scale. Now, for a 60% model, the volume of material that you need to make the parts is 0.6 times 0.6 times 0.6, which is, in percentage terms, about 21.5% of the volume you'd need if you were making a real part. And the same applies if you take a block of material that's the right size for machining a part from, say, a block of metal, then the same rule applies to how much metal you have to remove from your block. So the cube of the scale, if you like, that 21% for a 60% model, relates quite closely to the cost of making parts. So model testing costs you much less to make the parts. Another reason why teams used model testing is that in truth it wasn't possible until, let's say, relatively recently to put a race car in the tunnel and do realistic testing with a moving ground system, let's say 12 years ago. So before that, model testing was also actually more accurate than real car testing, because you're able to do a proper ground plane simulation, which with a race car in the past wasn't really realistic. But now it's really a cost thing that had kept teams using scale models. Now a 50% scale model would need only 12.5% of the volume of a real car. So, and that's about 70% more. If you started with a 50% model, you'd need about 70% more material to make parts for a 60% model. But on the balance of all the things you need to have a good simulation, we feel that a 60% model is about the best compromise between the accuracy of the simulation you do and the cost of it. And the rules have now banned a lot of the research methods we used to use. Straight line aero tests, putting a one-to-one car in the wind tunnel, they're now effectively eliminated from our, if you like, menu of things that we would want to do to develop the aerodynamics of the car. And one-to-one testing was unpopular with some of the Formula One teams because they didn't have that capability. So the teams like us who had that capability were seen as having an unfair advantage, and that's one of the reasons this was banned. All teams are able to do at least 50% scale model testing. This bit's going to involve some mathematics. We'll talk a little bit about what happens with 60%. How do you scale that up to 100%? But don't run away. The maths won't take long, and it's not so difficult. To translate from model forces to real car forces, you have to multiply the forces by the square of the difference in scale. So don't be too scared. So anyway, a 60% model will measure 36% of the real force. So you need to multiply forces up by 1 divided by 0.36, which is 2.7778. And this is easy to explain because the model is smaller and narrower than the real car. So a real car would be longer and wider, but the pressures, the forces, if you like, acting on a real car at the same speed will be very, very much the same. So you are increasing your area by a factor of the model scale squared. If you're testing, say, at 50 meters a second, and we want to assess the forces at a lower speed, say 30 meters a second. So 50 meters a second is 180 kilometers an hour or 112 mile an hour. And you want to assess at, say, 30 meters a second, which is about 108 kilometers an hour or 67 mile an hour. Then you have to divide by 2.778 again. Lucky, hey? And again, that is the square of the speed. In the end, it's just a matter of a little bit of mathematics. So we can scale from a model of almost any size to a real car and calculate what the forces will be on the real car. Now, there are some secondary effects that we'll talk about a little bit later, but not in too much detail, because then you're getting into things that I don't really want to talk about too much. Other people might be watching. Now, aero research is limited today both for the wind tunnel and for CFD. With CFD, we can only use a certain amount of compute capacity while we're doing our calculations, and the equivalent in wind tunnel term is wind on hour. So the amount of time you spend in the tunnel with actually the wind running. And we can exchange between the two, and we add up what we call units. So we have a limit of 30 units at the moment that we add up. Before the limits were imposed by the FIA, some teams averaged about 300 runs per week in their wind tunnels. Today, research is really quite significantly limited. The track testing is limited, straight line and wind tunnel testing for one-to-one cars is banned. We can test with a model up to 60%, and we can only test to 50 meters a second in the wind tunnel. And we're also limited then to 80 runs a week and 60 hours per week in the wind tunnel. So if you like, when you start your first run at the beginning of the day, the clock starts. When you finish your last run at the end of the day, the clock stops, and you're allowed to do 60 hours. So 60 hours would be 5 12-hour days, something like that. The wind on hours and the number of teraflops, we calculate the number of teraflops of compute power that we use for CFD calculations, are added up, and that sum must not exceed 30 units. And each team will split their units differently, but you could say that 15 wind on hours and 15 teraflops of CFD, 15 units each, if you like, is a reasonable estimate of what teams might do. And what teams will do will vary depending upon the strength of their different types of resources. Now, for 2015, the number of units drops to 25, from 30 to 25, and the number of runs drops from 80 to 65. So there's an additional reduction, and how teams split this, again, will depend on the strength of their individual resources, where they feel they're the strongest. But I'd expect that at least 10 units would be spent. By the vast majority of teams will spend at least 10 units in one, and perhaps up to 15 in another. Now, our wind tunnel can run to nearly 300 kilometers an hour. That's over 80 meters a second, or 186 miles per hour. Being limited to run to a speed of less than 180 kph, 50 meters a second, means we're downgrading, or we've effectively been downgraded to the same speed capabilities of, if you like, lesser wind tunnels. And that means we can't investigate the implications of things like higher Reynolds number, higher speed or scale, if you like, higher Mach numbers and things like that in the wind tunnel anymore. But of course, the same applies to every team, and that's definitely an area that I don't really want to say too much about, because other people are listening. You never know. Okay, Tech Bytes viewers, I hope you've learned a little bit from watching these videos. Please give us the thumbs up if you enjoyed our video series, and subscribe to our channel if you want more insights. If there are things you'd really want to know, please ask the question. You never know, perhaps we'll use your question to do another feature. And that's it for now. Bye.